to Speaker Night at the David Dunlap Observatory online with the Royal Astronomical Society of Canada, Toronto Centre. My name is Denise Chilton and I am the RASC Toronto Centre DDO Committee Chair and an operator of the 74-inch telescope at the David Dunlap Observatory. Together with Ward LeGros, who will be monitoring our YouTube feed tonight, I'm delighted to be your host for tonight's lecture. I'm also very excited to welcome you, our viewers, to tonight's lecture. Please take a moment to say hi in the YouTube chat and let us know where you're joining us from. This helps us make sure that our technology is working properly. The Royal Astronomical Society of Canada's mission is to enhance understanding of and inspire curiosity about the universe through public outreach, education, and support for astronomical research. In partnership with the City of Richmond Hill, RASC hosts outreach activities at the David Dunlap Observatory, or DDO. The observatory is home to this, Canada's largest optical telescope. And while we miss welcoming guests to the DDO facility, we are happy to bring you virtual programming instead. We would like to start by acknowledging that the David Dunlap Observatory in Richmond Hill stands on the traditional territories of the Wendat, the Haudenosaunee, and the Anishinaabe peoples, whose presence here continues to this day. We would also like to acknowledge this land is at the meeting place of two treaties, the lands of the Mississaugas of the Credit and those of the First Nations of the Williams Treaty. We thank them and other Indigenous peoples for sharing this land with us. It is my pleasure to introduce our speaker for tonight's lecture, Dr. John Moores. Dr. Moores is the York Research Chair in Space Exploration at York University. Despite frustrations with a tiny department store telescope in his youth, John chose to pursue a bachelor's degree in engineering science aerospace from the University of Toronto and later a PhD in planetary science from the University of Arizona's Lunar and Planetary Laboratory. He is a member of the Royal Society of Canada's College of New Scholars, Artists and Scientists, as well as a participating scientist on the Mars Science Laboratory, MSL, mission, popularly known as the Curiosity Rover. After training on MER, the Spirit and Opportunity rovers, in 2004, he contributed to the 2005 Huygens mission to Saturn's moon, Titan, and the 2008 Phoenix mission to the Martian Arctic. Dr. Moores is the director of the Technologies for Exoplanetary Science, NSERC CREATE program, a member of the Canadian Space Agency's Planetary Exploration Consultation Committee, the Canadian Meteorological and Oceanographic Society's Scientific Committee, and is the Associate Dean of Research for the Lassonde School of Engineering. Tonight, Dr. Moores will be discussing the cinematography of the sky and explore some of the amazing things we've learned by making films in space. If you have questions for our speaker, please post them in the YouTube chat. You can post them throughout tonight's talk. Dr. Moores will have time to take questions at the end of his talk. So please join me now in welcoming Dr. John Moores.
Well, thank you very much for that kind introduction, Denise. And thank you to everybody out there for choosing to spend your Friday night on such an unseasonably warm night here in Toronto with us. So tonight, I'm hoping to share a little bit with you about my work, making movies on other planets. And really, as far as I can remember, back when I was a kid, I really had a couple of different things that I just really fell in love with. So space exploration was one of those things. And on the other side, there were movies. There was just something about losing yourself in a story in a darkened theater alone with several hundred other people and maybe a little bit of oversalted popcorn. You can just imagine the experience, and hopefully we'll all be able to get back to something like that soon. So I thought it would be interesting, to think about something that combines both of these things. And where better to start than at the start of modern cinema with the Voyage dans la Lune, which you can see here, this iconic image of the man in the moon with that spaceship in his eye from the Jules Verne novel and as realized in 1902 by George Méliès. Now, with movies, the reason they're so compelling is because they're dynamic. Things are happening, things are moving. You wouldn't necessarily think the sky is the best place to think about movies. In fact, for a long time, people actually referred to the star field that we see in the sky as sort of the fixed stars. They were perfect. They were unchanging. And they were completely predictable. But, it's an idea that can go a little bit too far, to be honest. And I think sort of the worst bit of this is this idea that, all of the objects in the heavens, whether or not they moved around or not relative to one another, were these perfect, ideal things. You even got to the point where people started to think that the moon was itself a reflector, which is preposterous because you can look at it with your own eyes and you can see that it's not perfect. Folks even thought, at least in part, that perhaps what the moon was reflecting was the planet Earth. And so you see in some of these maps from 1,000, 1,500 years ago, the idea of, you can almost kind of squint and imagine this reflection going on. Now, granted, that would have been a real surprise to most cultures, and especially older cultures, because something that human beings have been doing for tens of thousands of years is looking up at the sky, using that to learn about the cycles that we have in the natural world. So when would you plant? When would you harvest for the best yields? Things like that. But also we told ourselves stories about the sky. And you have all sorts of people doing this all over the world, from the Mayans here with the Dresden Codex through to early Europeans with Stonehenge, a great big device for understanding the periodicity of movement in the sky. And then you have the Australian Aborigines down here who imagined constellations, who actually have a wonderful oral history of things like supernovae and whatnot. To all of these cultures, the idea that things in the sky changed and moved and were variable is nothing new. And by the time Galileo came around with his telescope, that concept of perfect, unmoving heavens was shattered. You had just to look with a telescope at the terminator of the moon, and you can tell that it's not a reflector. The moon has mountains, it has valleys, it has plains. You can see, if you look at it carefully, that there are some areas that are lit up that are beyond that terminator because they're higher than other things. Meanwhile, the phases of Venus, which you can see twirled around here, show that the sun was actually at the center of the solar system. And finally, looking at Jupiter, and there's a lovely animation up there, the first of what will be many animations in this presentation, you can see that not all objects orbit around the same central point. You've got motion around Jupiter, as well as motion around the Earth, motion around the sun. So now we know there's going to be motion, there's going to be exciting things that we can do movies of, make movies of in space. So we're ready to go, right? We're ready to, go get our crew, get all of our equipment, and, just jump out. Well, there's a bit of a problem here. The problem is timing. Not everything in the sky moves at a human pace, at something that it makes sense to make movies about. So we need to take a minute here and to think a little bit about the different time scales for things that are happening in astronomy in the sky. And I'll get a little bit of help on this one from a character, those of you who may have been doing some streaming during the pandemic may have seen. This is Miss Minutes. And what we have here, I promise there will be no graphs in this. It's a Friday night after all, but I hope you'll bear with me through a simple bar here. What we've got down here is a bar that shows things that happen very quickly, so fast at this end, and things that happen slowly at this end. And I'm going to show you a bunch of different processes that happen in an astronomical context, and we're going to have a look at the timescales on them. So let me put some markers down so that we can orient ourselves. This would be what we call a logarithmic scale, so it moves in powers of 10. So what you've got down here on the top, I've put down seconds, going from 1 millisecond all the way up to essentially the age of the universe. It's 10 billion years or so up here, to order of magnitude the age of the universe. And then the years are down there at the bottom, just to correspond. And I've noted a few simple things on here. So we've got, a millisecond out here, a second right here in the blue. By the time we're into green, we're talking about an hour. Sort of the green into yellow is a year. Out here in the yellow-orange is a million years. And then way on this side in the red, that's 10 billion years. I can put a few things on here to help orient you a little bit more. So if we think about the shutter speed of a fast camera, that's about a millisecond. Our heartbeat, that's about a second. An hour, that's about the amount of time you're going to spend with me tonight. So I have my picture there. It takes about a year for the Earth to go around the sun. So that's where I put that down. And for geology, it's about a million years. For the age of the universe and for large-scale cosmological processes, we're talking about billions of years. I put a very special marker down here. You see this woman with the mortarboard. This is the most important time scale when it comes to research in the sciences, because that's the length of time, 4 to 6 years, that one spends in graduate school. And an individual project usually lasts about the length of a graduate student's career. If you go much beyond that, it's a bit difficult to get things done. So let's replace these images and put down some processes. So the fastest things that we have in astronomy are things called fast radio bursts. They're way over here. They usually last around a few milliseconds. So they're very fast. You've also got on the far side that galactic evolution, which takes of order the length of the universe. And then everything else sort of falls in between. Pulsars, if you think about those, an individual pulse from a pulsar tends to last of order a few milliseconds up to, for the slowest ones, around 20 seconds or so. Supernovae we think of as these really fast things that happen, these big violent events. They can't actually happen much faster than a few tens to about 100 seconds, and their effects are typically felt for a few decades. So for instance, there's a big supernova in 1989. We're still watching that decay. And there are other things in here as well. The gravity waves that LIGO detects are here in the hour range. Weather here on the Earth, which is often something that astronomers are trying to avoid, but on other planets we really want to see it. That's here in the hours to days. Comae around comets, we see that evolve over the course of days. And there's a few other things in here as well. The orbits of planets, the time we go through a solar cycle with sunspots, about 11 years. Over a few thousand years, you can have change in the orbits of planets, and you can have proper motion. Something very fascinating I find about the ancient zodiac is that the Earth has precessed, its axis has changed enough that everything has moved around by about 2 signs of the zodiac. So astrology is actually about a couple thousand years behind where it really should be. We've got the Great Red Spot that's been going for about 400 years down here. And then we sort of fill up the end here with our stellar and planetary lifetimes, which are again of order billions of years. So not all of these processes are really set up for making movies. What I can show you here is that the best movies, and these are really clustered strongly around this sort of green area, this is the time scale of human perception, medium scale. So the idea is these are changes that we can understand as human beings. And anything that is shorter than that, down here in the purple, these things we need our technology to help us with. We can't perceive them, but the technology can help us to understand and to see what's going on. You may have seen movies of how the universe has evolved and things like that up here in the red, the large scale stuff. That is typically where we have those simulations or where we see inferences from large families of different static observations. And then we sort of put pieces together using our scientific method. So the best example of something like this would be something called the Hertzsprung-Russell diagram. So if you're a keen observer of stars, all of the stars have different colors to them, going from the sort of blue-white ones to the, sort of darker reddish ones. And what's kind of interesting is that it takes a long time for a star to evolve. It can take billions of years for a star to evolve. Even the shortest lived stars take thousands of years to get through their lifetimes. So there's no way for us to take a picture of an individual star and to watch it change. So what we do is we take pictures of all of the stars in the sky, we put them on a diagram like this, and we infer the way in which they actually change, that you work your way up the main sequence, that, perhaps you get stuck out on that sort of supergiant branch, for instance. So that's something that, we can see. And we can take our knowledge of that and put it into a computer with our understanding of gravity and make simulations. So what you're seeing here is a movie in effect, but it's all an animation. This is two galaxies colliding with one another over the course of billions of years, basically, hundreds of millions to billions of years. So it's a pretty picture. It's fun to look at. It gives us some concept of how this works, but it's not really showing us an observation. It's not a movie that really gets to you the way that some of the other movies out there do. Now, this is what we would imagine if we could speed up the clock. There are things we can look at that are on a smaller scale. So let me show you three other movies that are based on observation. So here, in the blue on the left-hand side, we've got an animation of planetary motion around another star. This is HR 8799. So these are orbiting exoplanets that were detected by the Gemini Space Telescope. And you can see them move over the course of a number of individual observations. The dates you can see down at the bottom. It's over the course of a few years or so. We can also watch how a comet changes over months. And you can see that in the upper right there. That's comet K5 Linear. In the lower left, in the lower right down there, you can also see Voyager on approach to Jupiter and see all of the churning and boiling motion within Jupiter's atmosphere. Now, the one thing I'll draw your attention to here is that all of these are planetary scale processes. So that tells me that an excellent place to go and make movies is actually on other worlds. Hopefully I have convinced you in this sort of long-winded 15-slide way that the best astronomical movies are going to be the ones that we make on other planets. And, don't forget, the planets were exempted from the whole unchanging perfect heavens at the start. The word planet actually comes from the Greek for wanderer. They were the ones that, were not following the pattern. And there actually are real movies from other planets. I'll show you a few of those. The poster that you see there at right, that isn't something made up. That's an actual film from 2006 that was made using a lot of footage that was taken from the Mars exploration rovers. And not a half bad 40 minutes, let me tell you. So we're going to go to planets. We're going to look at their movies. And what elements do you really need to make that good movie, to make it really pop? Well, you're going to need a dramatic setting first. We're not going to go to somewhere boring. It's not going to be as interesting. We need to have a story. The place has to have that background. We're going to have some appealing actors. We're going to have a well-trained crew. We're going to have the right equipment to make the movie in the first place, and then maybe a little bit of movie magic. So I'm going to talk about these in the context of a few different places where I've been involved with exploration. And the three of them, two are on Mars. So we've got in the upper right here, that is the Mars Science Lab, the Curiosity rover. It's not actually a picture of it. This is a simulation in the computer as well, but it has taken selfies of itself, and I'll show you one of those later. We've got the Phoenix lander, which is in the lower right, and we've got Cassini and Huygens in the left-hand side there. So we'll take a look at everything we've seen. So let's start with Mars. So welcome to Mars. Mars is really, to my mind, the exotic wrapped in the familiar, the land of blue sunsets, whereas we have red here. And everything else about this scene, other than the blue sunset, is something that I feel you can relate to. You can imagine yourself sitting in a lawn chair out in the desert watching the sunset. It's just that here, the sunset's blue and the rest of the sky is red, as opposed to on Earth, where you have kind of the opposite of that. So what I find really interesting about studying Mars and being involved with Mars exploration is that there's really sort of two different kinds of scientists. There are the environmental scientists like myself. We look out at the Martian plains. We look at the planet as it is today, and we see the blowing dust. We see the scudding cloud, the accumulating sands, and we love it. But the geologists are thinking about Mars's deeper story. They're looking at that history that's written in the rocks. And Mars's story really is one of gradual loss of water to space. So there's really those two different Marses, the Mars of today and the Mars of the past. And we can imagine back to where they might become one. If you take a look at this image here, this comes from the Spirit rover, and you take a look in the upper right, I'll highlight that with a red box. Just focus in on that, maybe even that little cleft rock, and I'm going to change one little thing about that red box that will make it appear much more Earth-like and give you an idea of the possibilities of ancient Mars. Let's just add a little water. And now it's not like you're in the desert anymore. Maybe you're on the coast of Mexico looking at a nice lagoon in the Pacific. So back in the past, Mars was a very different place, and its story is how it moved from being a place like that to what we see today. Spirit and the other opportunity, the two Mars exploration rovers, saw a lot of stuff. I really love this movie that they took of the dust devils. You can sort of see it moving along the ground. There are examples of movies like this where you can see up to 7 different dust devils, so it's a very dusty place. But at the same time, you see that evidence of water as well. And we really wanted to know what's going on with the water story today. At places where we are with the exploration rovers, with the Spirit and Opportunity, they're both very dry places, very equatorial. So if we wanted to see today's water, we needed to go north. And when you get as far north as Phoenix Lander was, even a little further north, you can actually start to see water on the surface in the form of ice. So this is the edge of the ice cap that I'm showing here. You can see that icy surface off to the left-hand side. And that little puff of dust you see there is the collapse in the side of the wall there. A little bit of dynamism in this particular image. Even if you get off the cap, the ice is never far. The dust itself provides a really effective way of protecting that ice. And I've shown in the little inset at lower right here that anywhere where you see a warm color, like a yellow or a red, those are actually places where the ice is within centimeters of the surface. So we didn't have to go to the cap itself, which is a very harsh environment. We could stay off the cap a little bit and just dig into the ground and take a look at the ice and try to read the story written in ice. But of course, you've got to get there first. And getting there, the voyage, the journey, as we know, is half the fun. And usually most of the movie, to be honest. So on the side of our Science Operations Center, which you can see down here at the bottom, we actually had a mural that depicted the story of Phoenix getting to Mars. And you have the launch over here at the Earth. Then you have the transit to Mars, which is actually very quiescent. There are no flaming horsemen or chariot riders or anything like that involved. But towards the end, as we go into the atmosphere, you've got the 7 minutes of terror as the spacecraft slows down from 6 kilometers a second of speed to 0, sitting quiescently on the surface. And that is a process where everything's got to go right. I'm not going to show you the Phoenix descent simulation, but I will show you some stuff from Titan a bit later on. Everything did go right, so it was all great. We even had a lovely telescope in orbit that turned around and took a look at where Phoenix was coming down. And if you were to zoom in on this pixel here, or that bunch of pixels in that little square, you'd actually see the Phoenix lander sitting on its parachutes. The white thing up on top is the parachute, and then the lander itself is the smaller white dot. So getting to Mars, an exciting journey. And then when we got there, oh my, we knew right after landing that we had hit pay dirt, or at least pay ice. Looking off to the horizon, that image that we've got at the right here, this is the first image. And that patterned ground, that polygonal terrain we call it, that tells us that the ice is very close. You only see that kind of pattern on the Earth when you have really ice-rich ground in the Arctic. And this is all around us. Once you do a complete panorama, you see it everywhere. And so we wondered, we came down on thrusters. Thrusters tend to move away dirt. Could we have exposed ice underneath us? And it turns out we put the imager down there, and yes, we did. We did see the ice directly exposed underneath the lander. That one is called the Holy Cow Mosaic because we had worried that we land in a place where, you know, the ice was too deep for us to get to. The answer, no, it's right there. So that was a great way to start the mission. Over the course of the mission, we were able to build up the story of what was going on in the Martian Arctic. You had this pattern, this picture that emerged of ice just below the surface. It sublimates, that travels up through that rocky soil, and then it gets mixed with the atmosphere during the day. At night, things cool off, and you get clouds. And you can see the clouds here in this image. It's all of these sort of warm colors. It's a little bit like a radar image, but with a LiDAR, which is with light instead. Those clouds make big particles. The particles form those clouds and fogs, and they snow out onto the surface. And you can see that snowing out when you take a picture of the LiDAR beam itself, which is what's being shown over here at the right. It's almost like a great big flashlight, or, you know, if you shine a laser up on a foggy day, you're going to get that column of light. And I find it really fascinating. The LiDAR was actually Canada's contribution to the mission. It's the one that discovered the snow. So it was very nice, I think, of NASA to bring us on board, a bunch of Canadians, to find some snow on another planet. So once that snow falls out, it turns back into vapor. That vapor goes into the ground, and it begins the cycle once again. So that's sort of the story of this area. Now, what about the actors for this particular drama? Well, often the first thing that gets personified in any one of these missions is the rover itself. And if you have any doubt, do an image search for cute rover, and you will find so many examples of this thing. There are even artists out there who will modify the actual hardware, MSL, or the Phoenix lander, or my personal favorite was one done with Cassini. And you can see what what people do. They get a real attachment to this spacecraft hardware, which is really quite adorable. Sometimes it's not just a spacecraft. Sometimes it's the planet itself. We've all seen images, you know, if you've been around for the discovery, or not the discovery, but the exploration of Pluto, of Pluto's heart. You know, just how wonderful was that you actually could see in the images the heart, and people have added, you know, a little bit of art to it as well. This one is probably my favorite. Maybe it tips the scale over the top on the cute factor a little bit. But I have an antidote to that, because, you know, we don't always feel this way. Sometimes you feel like the universe is just against you. And there's an image from Juno that's been modified that just tells that story oh so well, let me tell you. Angry Jupiter. It's not just the whole planet, too. Scientists actually, when they are exploring a place, will tend to name things. And we're naming things for convenience more than anything else. So here's an example of the landing site of the Mars Pathfinder in the late 1990s. And you can see that the rocks are all labeled here with various names. And the reason for that is that it's easier to recall a name than it is, say, an alphanumeric number. It's easy to say, you know, oh, go and, take a picture of, Squash Rock, rather than of rock, A571129X, right? So it's something that's very helpful to the team. We didn't have any experience with this on Pathfinder, so you'll see a lot of names here that are technically copyrighted. Later on, we changed and ended up taking inspiration from various places. So sometimes it was from stories, sometimes it was from maps. MSL's big on maps, Phoenix was big on stories, and other meaningful things. So here was what's called a workspace for Phoenix. And a lot of these come from Alice in Wonderland. So you can see, the cupboards there and other things of that nature. So the trenches that we dug and whatnot. And, sometimes what I love is that the public really gets in on the fun of naming things and of making the landing site come alive. So I like to think of these trenches here as the cast, but of course with Phoenix, there's also the cat. There was a well-wisher, an enthusiast who was not part of the mission, who imagined this whole story, and it's still up at stevethecat.com, of his cat traveling to Mars with the Phoenix lander and following along with it. And it was just lovely. I mean, those of us on the mission would actually go and see what this person had written that particular day. All right. You've been waiting for movies. Let me show you a few movies that we took on the Phoenix landing site. So here's 3 of them. And I've picked 3 very different ones for a reason. Each one of these tells us something about what's going on at the site. So if we start all the way over to the left here, I would like you to pay close attention to this area in the trench to the lower left. And what you'll see down there, if you look closely, is that there's a bunch of little pebbles that are there in one frame and gone the next. So they're deep down in the trench. They're not getting blown away. What's happening is that these are chips of ice. And over time, as we sort of auger these things out, we take them out with a scoop, these chunks of ice evaporated away and disappeared. So what this is telling us is that the white stuff that we saw underneath the rover, because we were very cautious at the time, and Jon Stewart made terrible fun of us for it, but that white stuff was actually ice, which is what we had come to see. So this was confirmation in a movie that we had found what we were looking for. In the middle image here, what you see is an instrument called the telltale. So this tells us about the wind. We have a little bob on a string, and we would watch how the wind would move it one way or another. You can see sort of an X on the mirror below it. So there's a little mirror, if I can show it. Oh, maybe it's coming. Maybe not. So the, so the center one there, you can see the wind moving around that little telltale bob. And that tells us that the atmosphere in this place is pretty quiescent. It's not blowing a gale or anything like that. And then the right-hand side, what you can see is an actual snow out event. So you see a cloud that appears, and then you see it separate into 2 pieces. And the lower piece, those are the ice crystals falling down. The movie is sped up a little bit. You can see the time counting off on the bottom there. But we actually see that snow falling in a way that we can recognize as human beings. Now, I did promise movie magic. And the magic that me and my group tend to use is a little thing called unchanging frame subtraction. What it does is it's a technique to bring out additional details. So we can capture lots of frames. This is a reason for taking a whole movie. And what we can do is we can separate the movie out into what's called a mean frame or the average frame, and that shows everything that stays the same. We can then take that frame, subtract it out from everything else, and what you're left with are the things that change. Naturally, that is a bit of a grainy image, but it really brings out the detail of very thin cloud. So I can show you what happens when we apply that to a bunch of movies we took at the sky. And often these movies would appear to be featureless at first glance, but you apply this technique to them and you get all manner of clouds. You get wavy clouds, cumulus clouds, streaky clouds, all kinds. We had a fairly small imager on Phoenix. We couldn't take images terribly quickly. So when I show you the Curiosity ones in a few minutes, you'll see how the technology improved and we actually got some better products. But it was so exciting with Phoenix. There was so much water cycling through the atmosphere all the time that on almost any day, you could point the camera up, take 10 minutes of footage, and you could get something wonderful like this. something that I think we can all kind of, relate to from a day just sitting on our backs on a grassy field, staring up at the clouds, just watching them go by. And of course, none of this happens without a skilled crew working in the background to develop and build the hardware that we need to do this kind of thing, and really to deliver it safely to other planets and then operate it on those other planets. And really, I've got to say, it's one of the greatest honors of my life to count myself amongst the crew of several different robotic planetary missions now. All right, on our way to curiosity, I'll take a brief intermission here and talk a little bit about the evolution of planetary cameras, because this is something that has improved with time. But please keep in mind the spacecraft technology, we don't select it for the same reasons that you would select a camera at Best Buy. We select the technology to be robust, to be resistant to radiation, and to the harsh conditions of space. And as a result of that, you end up with something that, in terms of its performance, is well behind the kinds of specs that you would expect from modern technology. So, for instance, if we look at the most recent example, the Mastcam Z, which is on Perseverance, you'll see that that is a 1200 by 1600 CCD. I think you'd be hard-pressed to find a 1200 by 1600 CCD if you went to the store and tried to buy the cheapest thing on the shelf. But this is an unbelievably reliable, robust camera. It's been calibrated so that we can do wonderful science with it. It's a great instrument. Moving back in time with Voyager, all those wonderful images came from scanning TV cameras, and those were 800 by 800 pixels. And my personal favorite from the earliest days of space exploration in the late 60s and early 70s, you've got the Pioneer spacecraft. The Pioneer spacecraft had 1 pixel. And you might say, how do you make an image from 1 pixel? Well, what would happen is the spacecraft would spin on its axis, and it would move in space. And so gradually, you'd be able to build up a picture just by scanning that 1 pixel across the sky. So you get your first images of a place like Titan using a 1 pixel camera from Pioneer. And I just love the ingenuity of doing something like that. So let's fast forward to Curiosity. We learned a lot about the water story of modern Mars up in the Arctic, but we came back to the equator to look more at the past story. And we've got better cameras down here. This actually is an image, or it's not a single image. This is actually a mosaic taken by the Molly camera, which is on the spacecraft's robotic arm. That's why you can't see the arm, by the way, showing Curiosity rover. The place where we landed, Gale Crater, it really is a land of lakes. We imagined this area might be a place that was wet at one point because we see minerals from orbit in the sort of moat around that peak in the middle that look like they were laid down in water, and then we see minerals higher up that look like they were laid down under more present conditions. And in fact, when we get there again, what we notice is that you don't even need any fancy instruments to tell you that this was once a lake bed. And you just look at all of those terraces of rock, evenly going off into the horizon down to the lowest part of that moat around the central uplift. It just screams, the remnant of a lake, even though it's a lake from billions of years ago. So the story of this place, I think, is quite clear. Nevertheless, there are still great things going on today. It's still a dynamic place. I love the dust devils. With the ones out at the Mars exploration site, the Spirit and Opportunity site, you only really saw the base of the column. Whereas here, because we've got all of these wonderful things in the background, we've got the mountain in the middle, we've got the crater rim, you can actually see the whole sinuous structure of the dust devils. And you can see that one just scooting around in behind the foothills there. We also see really great clouds because we've got very good engineering cameras that are able to discern very low levels, very fine details in illumination conditions. So we can take that mean frame subtraction method and we can take a look at the clouds over Gale. And even though Gale doesn't have nearly as much water in its atmosphere as does the place where the Phoenix lander came down, you still see all of these wonderful patterns. The ones off to the right, these are kind of cirrusy-like things. We would call them mare's tails on the Earth. On the left-hand side, you can see a sheet of what are called cloud streets, where you have all of these uniformly spaced rows of cloud just moving along. And we often see that here on the Earth as well. What it really is telling us about is about the waves in the atmosphere. And in fact, they're gravity wave clouds, not to be confused with gravitational waves, of course, but gravity waves, just like the waves in the ocean and whatnot, because you'll have air that has lots of moisture in it. It rises up and it cools and it forms a cloud, and then it comes down and it warms up and that cloud evaporates. So it gives you a pattern of clouds and free air clouds. And then in the middle, you can see a combination of these things over the terrain. So wonderful things to see here, especially during what's called aphelion season, when Mars is far from the sun. As we go towards the end of the day, we get even more spectacular things. So these are twilight clouds, otherwise known as noctilucent clouds. These wonderful little feathery types of features, very, very high in the atmosphere. Possibly these could be carbon dioxide as clouds. We don't know. What I find really wonderful about these noctilucent clouds on the Earth have all these colors. They're pearlescent. And the clouds that we get late in the day on Mars are no different. Here they are in full color. So you'll notice you go through all the colors of the rainbow there. And that is happening because the individual particles within the clouds are very well sorted. So I find that just fascinating about these images, the idea that you can tell what's going on at the level of microns, of fractions of a millimeter, of individual ice particles in clouds located kilometers away from a spacecraft on another planet. So we actually know something about the tiniest particles of ice on Mars. Now, helping me decode some of this stuff, I have a good team as well, a good crew. These are my grad students. I've now got my own lab up at York University, and we all have a lot of fun working on the mission. We do operations work every day and contribute to what the spacecraft does. We represent environmental science quite frequently. And I like to think that we have a lot of fun doing it. Certainly, the photo that some of my students took in the upper left there while I was on sabbatical would seem to indicate that they are enjoying themselves. All right. To end, I'd like to take us all the way out to Titan. Titan is an interesting place. It's the only moon in the outer solar system that has a substantial atmosphere. It actually has a thicker atmosphere than the Earth does. And it's made of the same stuff, nitrogen. There is a difference to it, though. It's a much colder kind of atmosphere. And you end up with methane. Methane rain, methane lakes. It's the only other place in the solar system that actually has a liquid on the surface that creates clouds and goes through the whole sort of cycle. But Titan is a very arid place. It's really defined by the huge number of sand dunes. More sand dunes cover the surface of Titan as a fraction of its total area than any other body in the solar system. They're all lined up in these wonderful rows that move around the terrain in sinuous patterns at the equator. When you go to the poles, you get the lakes. You can even see the sun glinting off of some of those lakes. We've got one of those images over here. That's a glint off of the Kraken Mare, which is one of the largest bodies of methane on Titan. And the radargram being shown below that is of Lake Ontario Lacus, so named because the folks on the mission feel that it looks more or less like Lake Ontario, and it's about the same size. So this is another really, really interesting place. And what I'd like to show you here is sort of the whole story of landing and exploring this world. We went and visited this moon back in 2005 with the Huygens probe. And I worked on a team there called the Descent Imager and Spectral Radiometer, or DISR for short. What DISR's mission was to go down sort of through the atmosphere. I'll just get this one going. We were going down through the atmosphere. We were on a parachute the whole time, and we were shooting images here and there and everywhere. We had a number of different imagers, some looking off to the side, some looking down, some looking up. We were taking measurements, looking at the sun, looking at the spectra so that we could understand, again, the very small particles of the titanium atmosphere. And what this video shows is all of those images as they're taken. They're assembled together into a movie of what it kind of looks like going down deeper and deeper into the titanium atmosphere. So you can see the spacecraft in the upper left there on its parachute over here. And you can see in green as we get closer and closer to the planet itself. So this is the trajectory that we're following. And you can see the individual images, each one popping up with a color, because all of the different imagers have a different color here. And you can see the planet getting closer and closer and closer. The drama is building, the tension and the storyline as we're getting our first view of Titan. Nobody had seen the surface of Titan before. It's completely enshrouded in this sort of, orangey haze. And so this was an exciting time. I remember being in the mission control over in Darmstadt in Germany. That's the European Space Operations Command Center. So we were watching these things come in. Unfortunately, it's not as ordered as we would like. We had a very particular way that we had arranged the image taking, so it would be nice and orderly. But you can see in this video that it seems kind of scattershot and haphazard. And that's because of an error that we had on board the spacecraft. The spacecraft sent back data on 2 different channels, but unfortunately, Cassini was only listening with 1 channel. Both were turned on, 1 was not set to record. And so there's only data that came back on that 1 channel that was set to record where we were really able to get information back. So that explains why it's a little bit scattershot, but we're still able to show you what it's like to go into the atmosphere, to go deeper and deeper. All of this stuff is much brighter than it would appear in person. Saturn is a very long distance away, almost, a little bit more than 9 astronomical units, which means that even at the top of the titanium atmosphere, the sun is going to appear 81 times dimmer than it does here on the Earth. And by the time you get below the clouds, you're into kind of a twilight zone of this sort of diffuse, hazy kind of darkness. So you can see that the ground is coming up now. We're getting a good view of where we are. And things are about to start happening quickly now in a few seconds' time as we get closer and closer to our landing site. Sometimes I just have to sit and watch this myself, remembering back 16 years ago when I was a graduate student. Now, I can tell you that the movie, hits its climax at that landing point, but it's not over once we get down on the surface, because there are still changes that can happen. Remember that the spacecraft has a lot of terrestrial equipment on board. All that equipment is heated up, and so it's a very warm object. Here we go, we're on the surface now. Parachute is down. Watch that bright light in the center column towards the bottom right, and you'll see it kind of shrink a little bit. So that has to do with us having landed on the surface, and we're starting to evaporate the methane that is in that surface. We sort of crunched through a bit of a creme brulee crust there, and then underneath things were, maybe wet is not the right word, but methane-y maybe. And so eventually we start to evaporate that. You can't see it in these images, but there's actually some fog banks that roll in and roll away in that tiny piece of sky. That's something that my team and I didn't realize until 2016, quite a bit later. So there you go. There's the story. And of course, afterwards, we have this wonderful scene of everyone who was there in that wonderful portable trailer on the ESOC site. This is an image that I took myself of the crew the science crew that was there watching this happen. And these are basically the first people who saw the surface of Titan. So of course, I can tell you I am really excited to see what Dragonfly does. And I've got a little shot there of Ingenuity, the helicopter from the Perseverance mission. But really, Dragonfly is going to be amazing. The kinds of movies they're going to be able to make, what they're going to see, be like nothing before. And the backdrop they've got, the drama of it will be wonderful. So we've had a lot of fun. What did we learn from planetary movie making? Well, it's really great for showing us the things that change in a scene. If there's a change going on, whether it's a dust devil going by, whether it's ice evaporating, whether it's a landslide, it tells us what's going on. And it can also help us to understand processes in the atmosphere. The atmosphere is uniquely set up to be understood with movies. We have movies of the giant planets. We have the movies that my group takes of Mars. And it tells us about the clouds, about the haze, dust devils, the falling snow. And I can tell you about how that improves the modeling of these atmospheres and how improving those models makes things like weather forecasting on the Earth better. But really, when you get down to it, it allows us to form kind of a human connection to the environments of other worlds. It makes them, make sense to us in our own minds, on our own scale, in a way that other measurements don't have the same kind of impact. And it's really for that reason that I love doing it and that I keep on doing it. So with that, we're at the end of the reel now, and I'd be happy to take any questions that you may have.
Thank you so much, John, for sharing these amazing views of space and some of the incredible things that we've learned by looking into space in this way and at planets in this way. Now we're going to check in with our RASC member, Wardla Grow, who has been monitoring the YouTube chat for your questions, for questions from our audience. If you haven't posted a question yet, now is the time. Ward, what have we got in the YouTube chat?
Yes, we have a few questions here. The first one is from Cicely. Great infographics. She's wondering if there's a chance we might have access to the Slow Fast series to start.
The Slow Fast series?
The Slow Fast series to start. That's the wording of the question.
Oh, I'm not quite sure what that means. I'm sorry.
Okay, Cicely, if you can put a clarification in there, I'll make sure that it's forwarded. Betty is also she mentioned, is there a story behind some of the names, i.e., Burn Alive?
Absolutely. You get these interesting choices because of course we've got the whole book of Alice in Wonderland and Neverland, Peter Pan basically, and you could pick anything from those stories. But one of the things with Phoenix that we were very challenged to do, it was one thing to see the white stuff on the surface, and then we saw it evaporate. So that gave us more confidence that it was water ice. But what we really wanted to do was to take that into one of our instruments that would then apply a lot of heat, hundreds and hundreds of degrees, to melt that ice cube. And then we could use the mass spectrometer to basically, taste and smell it and confirm that, yes, it is water ice. And so this was something that we had a monomaniacal determination to get that ice cube into the instrument. And so some of these particular trenches were chosen to find something to, bring into the instrument and burn. So that was the reason for picking some of those names.
Understood. Another question from Betty, is it known yet where all of the water where Mars went? Like the water from Mars, yeah.
Yeah, so most of it actually has escaped into space over geological time. And there's a reason for that. Mars formed very late in the solar system compared to other planets. That's what our simulations of the early dynamics are telling us. So Mars probably started off with less water than other bodies. So it didn't have as much as, say, the Earth did to begin with. but also the structure of the atmosphere of Mars, the lack of the magnetic field, makes it easier for that water to escape to space. And so you apply 4.5 billion years of time, and most of that water just sort of leaks away over time.
Okay. Eric Briggs had a question about the Dragonfly helicopter that is being planned to be sent to Titan. He was concerned how it will communicate with Earth, so he looked it up and said it will communicate directly. Is that
That's
right?
And most of our spacecraft do actually communicate directly to Earth, at least for some things. So with Curiosity, for instance, there is actually a direct Earth antenna there on which Curiosity receives commands. And if things go really awry, it can then send a signal back to Earth directly itself. Most of the data, it's easier for us to relay that off of the spacecraft that are in orbit. So when we need a big data transfer, we use that route. And when we absolutely have to talk directly to Earth for specific things, telemetry, instructions, then it's the direct Earth antenna. With Dragonfly, of course, there's not likely to be an orbiter in the Saturnian system at that time, so it's all going to have to be direct to Earth.
Oh, okay. And I had also one question, just wanted to ask in case anyone else had this question, is why the sunset on Mars is blue? Like, is that because of some of the gases responsible? And if so, which one?
The blue sunsets, yes. So it's actually the dust that's responsible. So the Martian dust, the way that from its shape, it actually is very efficient at scattering blue light forward, whereas the red light, it scatters off to the side. So what's happening is that the blue light that the dust scatters goes straight forward into your eyes, and the red light gets scattered into the rest of the sky. Because it's all particles that are doing the scattering, there's so little gas on Mars that if the dust fell out, it'd be almost black, the sky. You end up with this very strong effect, and it's most obvious near the sunset and sunrise when the sun is looking through the most atmosphere at the most oblique angle. The same way as, if you see those red sunsets, especially when volcanoes have put some dust in the air, you can see that most strongly towards sunset and sunrise when you have the most oblique path through the atmosphere.
Gotcha. And that's it for the questions.
Thank you, Ward, for relaying all of those great questions from our audience. And thanks also, of course, to John for answering them in so much detail. We've all learned so much tonight.